Well, good day there. This is Joe Van Cleve, and today I want to talk a little bit about hybrid lenses. These are kind of hybrids between glass refractive optics and pinhole optics. Stay tuned, please. So many of you guys are aware that I've been engaged in pinhole photography for quite a few years. Not as much in the last few years though, but I've done a lot of pinholing over the years. I've done a few videos about them, and a lot of you guys are interested in that. Now, I was watching a video recently of a landscape photographer who was using a 0-2000 pinhole camera. This is a medium format teak wooden pinhole camera, and he was doing some landscape photography with it, and I really love those cameras. They're beautifully built, and I like some of the images that come out of those cameras. But I was noticing that for a lot of the landscape images that have a lot of detail in them, like for instance when you're in the forest and all the little branches and the leaves and all the texture of the tree trunks, those kind of images with a lot of texture end up looking less than satisfactory sometimes when rendered with pinhole cameras, because all the fine detail is obscured by the softness of the pinhole lens. Now, I have seen some landscape images that are absolutely gorgeous with pinhole cameras, but these are usually like, for instance, seascapes, beach, soft wet sand and soft textures of seaweed, for instance, and rocks, and the moving water and the ocean and the horizon and the sky. The kinds of things that don't have a lot of sharp edges, they look just exquisitely gorgeous when rendered properly in pinhole. But I was thinking about this idea that when you're looking at landscape images, when you're in the landscape, first of all, as a person, you have this angle of view that's, whatever it is, 90 degrees, let's just assume for the sake of argument. And you can see that 90-degree panorama. But if you're holding a little 4x5 inch image of a landscape up to your hand, up to your eye, about arm's length, you're only looking at about a little sliver, like a 30-degree angle of view. It doesn't appear to be landscape-ish at that small scale. But when you enlarge a pinhole print, let's say, into such a size that you can get up close to it and get that kind of 90-degree angle of view as you're looking at the print, you end up seeing a lot of the softness of the image oftentimes with pinhole, simply because that's the nature of the image. So I've been interested in pursuing another optical technology that was used back in the 19th century, which is taking a glass lens, a refractive lens, and stopping it down to an aperture that's so small that it's almost the size of a pinhole, but not quite. It's bigger than a pinhole, but smaller than what you might normally use in large format. And that's what I'm going to explore today. So let's talk first of all about pinhole optics. And what I've done is I've made a very simplified diagram here. What you have is a very simple cross-section of a pinhole box camera. The pinhole has been exaggerated in size, and I have the focal plane or film plane behind here. And my object that I'm going to be photographing or imaging is a simple transition between a light colored part of an image and a dark colored part of the image. And if this transition was rendered in absolute sharpness, you would have a very crisp and sharp transition edge at the film plane. But what happens because of the so-called particle nature of light, as the rays of light project themselves through the pinhole aperture, you have this spreading out of this edge. And so at the image plane, you'll have the dark part of the image on this side, the light part of the image on this side, and instead of a sharp edge, you have some kind of a gray transition that's soft instead of a sharp edge over here. Now you can imagine that if you made the pinhole smaller in size, that this divergence of the light would be less, and this gray fuzzy region would be smaller, and you would have a sharper image. And you could imagine that as you start shrinking down the size of the pinhole more and more, you might approach a point where that was very sharp in appearance. But there's a limitation to how far you can do that. And let me show you what that is. And that involves what's called the so-called wave nature of light. So I have a large aperture opening here. And let's just assume maybe this is a glass lens for the sake of argument. And let's assume it's a fairly sharp lens and all the light is going through this opening and you're looking at the opening itself. There is a narrow region right around the edge of the opening within several wavelengths of that edge, where the light passing within that zone is going to be diffracted. It's going to warp itself around the edge and soften the image. Whether or not this actually affects the quality of the image depends upon the ratio of the area of the central part of light that didn't get close to the edge versus the area around this toroidal shape near the edge that did get diffracted. So with a large aperture, you have most of the area of light going through the aperture is not affected by the edge. But if you stop down the aperture to a very small size, let's say pinhole size, the distance of this exclusion zone is still the same because the wavelength of the light is the same. But now you see that the area of light that is affected by the edge, it looms much larger in importance than the central area that's not affected by diffraction. And so as you stop down the aperture smaller and smaller, diffraction becomes increasingly and more important. So you have these two different natures of light, the so-called particle nature and the so-called wave nature, and they're both competing against each other. And the way they do that is drawn on this graph here. On the vertical axis, we have sharpness. And in the sharpness category, it goes from soft to sharp. And then on the horizontal axis, we have the aperture size, and it goes from a wide aperture to a narrow aperture. Now, this is our particle nature of light as it affects the image sharpness. The narrower the aperture is, the more sharp you'll have it because of the simple projection principle. And as you widen the aperture, the sharpness goes down because the particle nature of light, the light bundles are going to be diverging. On the other hand, you have the wave nature of light, and if you have a very wide aperture, you have very little diffraction, and so the wave nature of light is not going to be degrading the image that much. But as you narrow the aperture down, you're going to have more and more diffraction, and therefore the effects upon sharpness will be more severe. So these two particular aspects of light in a pinhole system will optimize themselves at a certain crossover point. There will be a certain size aperture that will have optimal sharpness, a balance between the wave nature of light and the particle wave nature of light. And it's based on the focal length of the light and the focal length of the camera. Okay, so that is with pinhole optics. So in the early days of photography, lens designs were not very sophisticated. And the problem with simple single element meniscus lenses is they have really bad off-axis aberrations. And so the early camera makers discovered that if you stop down the aperture of the lens, you could get rid of a lot of these aberrations and make the image better. But if you stop it down far enough, the early emulsions, the early photographic emulsions were not sensitive enough to really render pinhole images, because the exposure times would be unmanageably long. So what we would like to do in this little project is find like a hybrid optical design. We'd like to use a simple refractive glass lens element, and we'd like to stop it down enough so that we can get rid of almost all of its aberrations, but not stop it down far enough to get pinhole type diffraction. And so you can kind of represent this by, as you widen the aperture wider than the optimal pinhole size, we want to continue to increase the sharpness due to the fact that we have a glass lens in there behind the pinhole. Now, if you continue to widen the aperture even more, you'll end up degrading the image eventually because of those off-axis aberrations that are part of these kinds of simple optics, like coma, spherical aberration, and chromatic aberration, etc. So there's going to be an optimal point here where we will be able to increase the quality of the image by widening the pinhole aperture somewhat with a glass lens behind it. I've chosen today to use my workhorse camera for this experiment. And I'm using a speed graphic, and this is a World War II era 4x5 press camera. And the important thing about the speed graphic for our purposes is it has a curtain shutter at the film plane. And it has two different settings. This knob that goes with numbers 1 through 6, and this knob that winds up with letters A through D. So if you wind up the curtain, you'll have, in this case, I have C2, and there is a brass plate that tells me that C2 is approximately 1/240th of a second. And then if you trip the shutter, that took a picture. So, why is it important to have a focal plane shutter? Well, because I'm using a simple lens that does not have its own shutter. A conventional large format view camera lens has a leaf shutter built on the lens. But what I'm using for a lens today is I'm using the front objective of a Bushnell 7x50 binocular. And I think this is a 2-element lens design, but it's not much better than a single element meniscus lens. And what I've done with this binocular is I've simply stopped it down to a 3mm aperture with a 3mm hole and a piece of brass that's been taped to a piece of cardboard and put on to the back element of the lens. Ideally, you want to kind of put it on the front so that it minimizes stray light coming through the rest of the glass and fogging the image, or if you have any defects in the glass. But it was easier for me to fit it in the back. So I have a simple model aircraft plywood lens board. It's about 4 inches square. It fits on the speed graphic. So I'm going to do several tests. I'm going to first of all take a photograph with this camera with the lens wide open. And this is about a 6-inch or 150mm focal length lens. And a wide open, it's 50mm, so it's about an f3 wide open. And you'll see how poor the optics are wide open on this lens. And then secondly, I'm going to stop it down to the 3mm aperture and take another photo of the same scene. And then thirdly, I'm going to be using a pinhole optic. I have a pinhole lens board. It's just a simple piece of masonite. And by the way, the Masonites were related to the Jebusites and the Levites and the Hittites, in case you were interested. But anyway, the Masonite board, I have a 1/4-inch hole in the front, and I have a little piece of brass with a pinhole taped onto the piece of gaffer's tape. And there's a spare pinhole right here. The pinhole I'm using is a 0.33mm, so 1/3 of a millimeter in diameter. And I was using the camera set to about 125mm focal length, a little bit shorter than this one, just so it wouldn't interfere with the front of the bed. So I'm going to take that picture to show you what a basic pinhole image would look like. And then I'm going to put the stopped down binocular lens back on it and take more of a close-up image and see what kind of depth of focus we have compared to the pinhole. So these 4 test images I made today were done on Arista, which is Freestyle Photos house brand. It's resin-coated grade 2 photo paper. These are paper negatives, so this being grade 2, the contrast of the paper is not dependent on the color of the light. And I have 4 images. This is my image from the binocular lens wide open. This is the image with the binocular lens stopped down to 3mm. This is the pinhole optic image, and then this is the binocular lens stopped down to 3mm, focused close up against the trellis in my backyard. And so I'm going to show you scans of all 4 of these, and we'll analyze these and discuss them. Okay, here is the wide open binocular lens running at f3, and you can see the very center part of the image near the top of the tree trunk is fairly sharp, but as soon as you get away from the very center, the image goes way wacky, and the further out toward the edge, the softer it gets. This is actually a pretty good effect for a portrait. Maybe you wouldn't probably want it this wide open, but if you stopped it down a little bit, it would make a pretty good portrait lens. But if for landscape purposes, generally speaking, it really is way too narrow and aberrant. And here we have the same binocular lens on the same scene stopped down to a 3mm aperture, and we can see that we're getting a lot closer to it being optimal in sharpness, and we've gotten rid of almost all of the aberrations off axis, except the very corners might be a little soft, you might be able to tell, but this is quite a bit sharper and better than before. This is a very usable image, and this is kind of what we're looking for with this hybrid optical system. Here is the pinhole image of the same scene. It's a slightly wider angle because the focal length was shorter, but on a cursory examination on a very small screen, this looks pretty sharp. But if you get up close and look at it on a bigger size screen, you can definitely tell this is a softer image. It's not nearly as sharp as the optimized hybrid glass small aperture system that we really want to work with here. So again, this is pinhole. It's better than the wide open lens, but not as good as the hybrid. Finally, we have the hybrid optical system focused close up to this trellis. It's about a foot away, maybe 12 inches away. And here you can see, unlike a pinhole image, you do have narrow depth of focus. The foreground trellis is sharply defined, but the background between the squares of the trellis you can see are soft. So there is some selective focus capable with this hybrid system if you're working close up, as we might be at one time or another. Well, my objective today in this project was to explore hybrid optics, a hybrid between refractive glass lenses and pinhole optics. And the idea is to make a focus-free camera that renders images sharper than pinhole with the same kind of simplicity. And this would be especially valuable for landscape images where if you desire to enlarge the image a little bit bigger than what a contact print would permit, or scan it and post it online where you don't know really how big it's going to be viewed at because you don't know the size of the viewer's computer screen, you'll get a little bit more sharpness out of it from a conventional pinhole because you have a little bit of refractive optics helping to sharpen the image somewhat. As I indicated earlier, these kinds of hybrid optics were used in the early days of photography in the 19th century. And I think it's an interesting idea, and I think there's some merit to building these kind of simple cameras with hybrid optics. Well, I hope this gives you guys some ideas for your own photography projects. Until next time, this is Joe Van Cleve, and you have yourselves a great day.